Okay, so we're going to continue talking about resonance structures. And these are some we're continuing to talk about Lewis structures. And right now we're going to talk about some examples that use double bonds, triple bonds, and then we'll talk about something called resonance. So let's just review what we know so far. So a single bond is represented by a single line. And it's sharing 2 electrons. So you'll either see it 2 electrons or a single bond sharing 2 electrons. So a double bond is when we're sharing 4 electrons. It's represented with 2 lines, double bond, sharing 4 electrons. And then the last would be what's called a triple bond. A triple bond is when 2 elements are sharing 6 electrons. It looks like this. It's called a triple bond. And then it's sharing 6 electrons. So we've done some examples with single bonds. Now we're going to look at some examples with double bonds and triple bonds. And once we start talking about double and triple bonds, we're going to see some examples of something called resonance. Okay, so let's look at the Lewis structure for carbon dioxide. So like I said in a previous video, most of the questions that you're going to see on the exam, it might say, draw the Lewis structure for carbon dioxide. And I would give you the name, and then from the name you would have to determine the formula. You would need the correct formula to determine the Lewis structure. So carbon dioxide means that I have 1 carbon and I have 2 oxygens. I know this is covalent because carbon and oxygen are both nonmetals. Okay, so we are doing the Lewis structure. So remember, the first thing that we need to do for a Lewis structure is we need to determine the total number of valence electrons. So what we're going to do is we're going to see how many valence electrons each element has, and then we're going to add them together. So how many valence electrons does carbon have? How many valence electrons does oxygen have? Times 2, and then that's going to give me the total. So again, you can determine the number of valence electrons based on the position in the periodic table. Carbon is in group 4, so it has 4 valence electrons. Oxygen is in group 6, so oxygen has 6 valence electrons. 6 times 2 is 12. So I have a total of 4 plus 12, 16 valence electrons. So these are the valence electrons that I have to equally distribute around this molecule to try to satisfy the octets of carbon and the 2 oxygens. So when you are trying to think of how am I going to set this up, we will learn about a rule that will tell us which way to set it up, the order of the elements later. That's called formal charge. For now, molecules will always choose to be symmetrical. So we would not do like this, COO, because that is not symmetrical. We also would see by doing something called formal charge that this is not correct. We'll talk about formal charge later. So anytime you can make the molecule symmetrical, that is what you should do. Also, you also should put the element with the highest bonding capacity in the middle. Carbon has a bonding capacity of 4, oxygen only has a bonding capacity of 2, so that's another reason why we know carbon goes in the middle and the oxygens go on either side. Okay, so we've drawn what we think it should look like. Then you connect the elements with single bonds. Then you distribute the electrons to try to satisfy the octets of all the elements in the molecule. So in these two single bonds, I have used 4 electrons, 2 4 electrons, and I have 16 total. So now I'm going to see if I can make everybody happy here. So you start by doing single bonds, and then you distribute around the outer atoms first before you come back to the central atom. So 2 4 6 8 10 12, 14, 16. Okay, so we've distributed all the electrons. So let's just look at what's happened here. So now this oxygen has a full octet because it's sharing these 2 electrons, and then it has 4, 6, 8 more. This oxygen has a full octet because it's sharing 2 electrons, so it has 2, 4, 6, 8 electrons. This carbon is not happy. This carbon wants a full octet. It wants to have 8 electrons around it. It only has 2 4 electrons around it. So when we do not have enough electrons to satisfy all outer shells, we use double or triple bonds. Okay, so we're just going to start with a double bond and see what happens. If I use a double bond, essentially what that says is I'm now going to share 4 electrons instead of sharing 2 electrons. Well, I was 4 electrons short. So I know sharing these 2 aren't going to get me there. So I'm going to need to share 2 on both sides. So now let's try this again, having double bonds connect the carbons and oxygens. Okay, so now I have a carbon, and I have used 2, 4, 6, 8 electrons. So I have 8 electrons left. So 2, 4, 6, 8, 10, 12, 14, 16. So now let's see. This oxygen has 2, 4, 6, 8 electrons around it. It's happy. This oxygen has 2, 4, 6, 8 electrons around it. It's happy. This carbon has 2, 4, 6, 8 electrons around it. It's happy. This is the Lewis structure of carbon dioxide. Carbon dioxide is 2 double bonds between the oxygens and that central carbon. Okay, let's look at another one. Let's look at something called hydrogen cyanide. So this is not an example of a name that I would expect you to be able to tell me the formula of. The cyanide ion is Cn minus, and then the hydrogen ion is H plus. So the hydrogen cyanide is HCN. Okay, so we still want to see the total number of valence electrons. So I need to know how many does hydrogen have, how many does carbon have, how many does nitrogen have, and I just have one of each of these. So again, based on the position on the periodic table, you can tell how many valence electrons an atom has. Hydrogen is in group 1, it has 1 valence electron. Carbon is in group 4, it has 4 valence electrons. Nitrogen is in group 5, it has 5 valence electrons. So 1 plus 4 plus 5, I have a total of 10 valence electrons. So I know I need to distribute 10 valence electrons around all the atoms in this molecule to have the correct Lewis structure. Again, you are going to put the atom with the highest bonding capacity in the middle. Carbon has a bonding capacity of 4. Nitrogen has a bonding capacity of 3. Hydrogen has a bonding capacity of 1. So carbon is going to go in the middle. Nitrogen is going to go on one side. Hydrogen is going to go on the other side. It doesn't matter the order. I just put it in the order that it's written in the name. Okay, so I have 10 valence electrons. So if I do 2, 4, I only have 6 valence electrons left. So I am not going to have enough valence electrons to fill both the octet of nitrogen and the octet of carbon. Hydrogen is already full because remember, hydrogen just wants a duet. So hydrogen with this one bond is already done. It's happy. Okay, so I've used 2 4 electrons and I only have 6 left to satisfy both these octets. So I know I'm going to need at least a double bond. So now let's see if we could make it work. So I've used 2 4 6 and I have 4 left. So if I have 4 left, I could put 2 4 on this nitrogen, and then nitrogen would be happy. It would have 8, but carbon is only going to have 6, 2 4 6. So I must need a triple bond. So now let's see if we can make it work. 10 valence electrons, I've used 2, 4, 6, 8. I have 2 left, and they're going to go right here. Now, everybody has a full octet, or a full outer shell. Hydrogen is a duet. Hydrogen is full. Carbon has 2, 4, 6, 8. It's happy. Nitrogen has 2, 4, 6, 8. It's happy. This is the Lewis structure for hydrogen cyanide. So when you have not enough electrons to satisfy the outer shells of all of the elements, you use double or triple bonds. So let's look at an example where we use something called a resonance structure. So I'm just going to put this right down here. A resonance structure is when we have unsymmetrical distribution of a double bond. So let me explain to you what that means. Let's do the Lewis structure for something called ozone. Ozone is O3. So it's 3 atoms of oxygen covalently bonded together. It would also be called trioxide. Or the common name is ozone. So let's see how many total valence electrons there are. So oxygen is in group 6, we already said, and I have 3 of them. That means I have 18 valence electrons. Okay, so I'm going to have oxygen, oxygen, oxygen. And I'm going to put 2, 4. I'm going to put single bonds there. So now I have 14 electrons left to fill the rest of these. So when we do this, we find out that we actually need 16 electrons because I would need 6 here, 6 here is 12, 4 here. Sorry, we have 2, 4. We've used 4, and we're going to need 16 more, but we're only going to have 14 more because we've already used 4. So I know I'm going to have at least 1 double bond. I'm only going to need 1 double bond. So you see this is asymmetrical. There is a double bond on this side and a single bond on this side. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. This is the resonance, this is the structure for ozone. What is true is that this is also the Lewis structure for ozone. This double bond is actually 50% this structure and 50% this structure. It's like they're vibrating back and forth, this double bond is actually half in both locations. When we get into biochemistry and organic chemistry, you'll see that it's kind of like half here and half there. But this is called a resonance structure. A resonance structure is when you have asymmetrical double bonds and both of these structures are correct. Most of the time you will see resonance structures in brackets like this. Anytime there's more than one position where that double bond could be, then you have to draw all of the positions to show the resonance structure. This up here, hydrogen cyanide, it does not have a resonance structure because you could not have a triple bond between hydrogen and carbon because hydrogen only wants to make one bond. So this does not have a resonance structure. This does not have a resonance structure because it's symmetrical. We only see resonance structures when there is unsymmetrical distribution of a double or triple bond, and then you would draw out both of those, and you're kind of saying the actual structure is the average of those two structures. So that's a double bond, a triple bond, and an example of resonance structure. One thing to mention that I should have mentioned here is that as the bond number increases, the bond length decreases. I'm going to write that down right here. Oops. As the bond number increases, the bond length decreases. So a single bond would be the longest. A double bond would be in the middle, and then a triple bond would be the shortest. So as the bond number increases, the number of bonds, the bond length decreases.